Hi, my name's Gabe. For this problem, we're asked to find the distance between the point 1, 3, 4 and the plane 4x minus 5y plus 2z equals 6. So let's begin by recalling what the distance between a point and a plane is. So the distance is equal to the magnitude of the projection of PQ onto some vector n. So what this is really telling us is that if P is a point on our plane, and Q is a point not on our plane, and n is a vector which is normal to our plane, well, the distance is the magnitude of this projection vector. And we know that this is equal to the absolute value of PQ dotted with n divided by the magnitude of n. So this right here is what we're going to use to find the distance between this point and our plane. So what we need to do is we actually need to go ahead and find a point which lies on our plane, as this point doesn't lie on our plane, so that we can find our vector PQ. And then we'll have to find our vector n, which is just a vector normal to this plane, which is pretty easy to find. So if we want to find a point on our plane, well, since c, the number that we're multiplying z by, isn't equal to 0, and 6 is a nice multiple of 2, well, what we can do here is we can say, let's let x equal 0 and y equal 0. And if we substitute 0 into this equation, well, what we have is we have 2 times z equals 6. Solving for z by dividing each side by 2, we have z is equal to 3. So what's this tell us? Well, this tells us that a point on our plane is going to be the point 0, 0, 3. So I'm going to call this point right here P, and I'll call this point that's not on our plane Q. So now what we can do is we can go ahead and we can find our vector PQ. So PQ will be given by 1 minus 0, which is 1, 3 minus 0, which is 3, and 4 minus 3, which is 1. So now we found our vector PQ, and all that's left is to find our vector n, so the vector which is normal to our plane. And since our plane is already written almost in the general form, if we wanted to write it in the general form, we could subtract 6 from both sides of the equation. It's not going to change anything, so we can actually write down our normal vector n, which is just the vector 4, negative 5, 2. And as I said earlier, if you wanted to write this in the general form, you would subtract 6 from both sides of the equation, but you would still see that the direction numbers are still 4, 5, negative 5, and 2. So now we have PQ and we have n. We can go ahead and find this distance. So the absolute value of this dot product is the absolute value of our vector 1, 3, 1 dotted with her vector n, which is 4, negative 5, 2. And this is all being divided by this magnitude of n. So we can just write down that magnitude of n as the square root of 4 squared plus negative 5 squared plus 2 squared. So in the numerator, we're going to have the absolute value of 1 times 4, which is 4, plus 3 times negative 5, which is a negative 15, plus 1 times 2, which is 2. And in the denominator, we're going to have the square root of 16 plus 25 plus 4, which is the square root of 45. So in the numerator, we're going to have the absolute value of 4 minus 15 plus 2, which is the absolute value of negative 9, which is 9. And in the denominator, well, the square root of 45 simplifies to 3 times the square root of 5 to 3, divided by the square root of 5. And at this stage, we can rationalize this denominator by multiplying both the numerator and denominator by the square root of 5. And what this leaves us with is the distance between our point and the plane is equal to 3 times the square root of 5 divided by 5. Thank you.